What we discussed in the last class was some introduction to the D algorithm, where we said that what are the steps that are required to carry out the D algorithm. Primarily there are three stages here. We have to generate the fault, propagate the fault to the output, and then ensure that we have a consistent set of inputs to perform this. So before we take an example and illustrate the steps, let me introduce some of the terminology that is associated with it. So we have what's called singular cover. I will take up each one of them. Singular cover, D intersection, primitive D cube of a fault, and propagation D cubes. Primarily all of them revolve around the singular cover. The singular cover actually is nothing but the truth table, which is written in a slightly compact form. Let me tell you one thing, that it's important to realize what's happening. So basically how are we proceeding from 2 points of view. What we are doing here at the gate level, as I said, you can apply the D algorithm for any other combinational circuit. As long as if you know the procedure, then you can generate all the other intermediate inputs required, that is the PDCF, PDC and so on that we are going to discuss. So of course for PDCF and PDC for gates you can actually do it even just by basic analysis. But this procedure is important because if you have a black box, let us say I want to apply the D algorithm on RTL modules, I can still do it because I know the procedure how to start from the truth table. Any combinational module will be characterized by a truth table. So once you know the truth table, I can actually apply the D algorithm. So singular cover of a gate or any circuit element for that matter is nothing but a compact version of the truth table. So if you look at the AND gate, what is that truth table for an AND gate? So there are two inputs and the output is. So if you analyze this AND gate, so basically if you combine these two terms, so you can write this as 0x0. Similarly, if you combine this with this, you can write it as, so it's nothing but writing these rows is nothing but writing the truth table in a slightly different manner, which is a more compact. So here I say that I don't care. So it's 0x0, A, B and are the inputs and C is the output, and x00 1 1 1. In case of a 1 I can't do anything because there is only one term, so there is. So this writing it in terms of the don't care actually helps considerably, because later on as we will see that that's very critical that I have enough don't cares to be able to ensure what's called the consistency. So I have this, so this is what is the singular cover. So similarly I'm showing over here the singular cover of an OR gate. Very similar. So if any of the inputs is 1, I don't care what the other input is and I get an output of 0. Similarly, if cross 1 0 and 0 0 1. These gates are symmetrical around inputs, but if you consider combinational logic, which is more complex, it's not necessary that they are symmetrical. For example, I can do the singular cover for a multiplexer. If I do a singular cover for a multiplexer, there are 3 inputs, A input, B input and a select input, and around A and B though of course the function is symmetrical. Okay, that's also not symmetrical because you have 0 and 1, you are selecting one with 0 and another with 1. Now as far as the select input is concerned, it's completely asymmetrical around it, so that's not necessary. So you start from a truth table and then generate the singular cover, and that is one of the starting points. And we have already seen how you can generate this, because look at the rows where the output is the same, and if you can eliminate one or more variables, eliminate that and put them to be don't care. So you can do it using the Carnot map method. If it's a very complex thing, basically from the Carnot map you can look at, if you consider all the inputs, they are the min terms, and those which combine will be able to use to eliminate some of the variables. So you can generate your singular cover in this manner. Then we define what's called a D intersection. Okay, D intersection, primarily the way we look at it is, when we are doing this D algorithm, we look at each of the circuit nodes to be capable of taking 0 1 x d d bar. We consider that each circuit node can take one of these 5 values. So, typically we say 0 or 1, so you extend it to 0, 1 x d d bar. What is the meaning of it? 0 and 1, of course. X is till now I have not assigned any value to it, I do not care till now. Of course, it does not mean that finally of course this x's will get converted, but if I do not care what value that node has, then it is x. D essentially refers to a fault. What D refers to is that under the faulty condition this node has one value, under the non-faulty condition this particular node has a different value. So, this value which is different could be either 0 under faulty and 1 under non-faulty, or vice versa, 1 under faulty and 0 under non-faulty condition. So, that is referred to as, if a circuit node takes such a value which is different for fault and in the presence of fault and without the presence of fault, then it is called D, that particular node has a value D. D complement is a complement. So, if it is a D is 0 faulty and 1 non-faulty, then D complement is the reverse. There is nothing absolute about it. You can say that you can define D in any manner, but you have to be consistent that if at one place it is D and another place it can be D complement, because its behavior is the reverse of the node that is under D. So, however you define D, so you have this flexibility of what you call as D, but once you show something to be D, you have to be consistent and call the nodes which are the opposite of it to be D complement. So, these are the 5 values, and how they, as they proceed in this with the D algorithm, the nodes will get specified with one of these 5 values, and we will see how it works. But the way the D intersection works is, I have 2 different specifications coming from 2 different sources. What is the final value of that node? What the D intersection specifies is, I can derive the value of the node by looking at, so one value may be coming, the columns correspond to one value, the rows correspond to, for the same node, 2 different specifications are trying to give 2 different values, what will be the final value, and that is given by the D intersection. If one specification is 0, another is 0, of course it is 0. If one is 1, another is 0, I am calling it D complement. But as I have already defined to you, you can completely change this notion, what you call as D and what you call as D complement. So, 0 and 1 is giving you a D, 1 and 1 is giving you a D. When it is do not care, you essentially get what you have written over here, 0 gives 0, 1 gives 1, do not care gives do not care. So, this is going to override do not care. Similarly, if you look at this particular row, whatever 0 gives 0 and do not care gives 0, 1 and do not care gives 1, and so on. These are not specified, and I should never intersect in a manner that I do not know what the value is going to be. So, basically you should avoid intersecting D with 0, D. So, you are not allowed to do that, because you do not know what is going to happen, it is not specified. All these are not specified, all these are also not specified. I have put a star over here. This star has a particular meaning. Typically what happens is, if you have to intersect D complement with D, you are not allowed to do it. But what you can do is, you can change the specification in such a manner that all D's become D complement, and then you can intersect. Because after all it is up to you, as long as you maintain a consistency in a specification that you have, you maintain this consistency, you can complement all D's to D complement, and D complement will become D's in that case. And then you can, after all, you can intersect D complement with D complement, so you change D to D complement and then intersect. So, there is some flexibility that is there, and that is why I put a star over here. Of course, this will be clear as we proceed with the illustration, but this is the D intersection which specifies how the node value changes if you have 2 different values specified. Okay. Now we talk of what is called primitive D cube of fault. When I have to generate a fault, I have to basically generate a fault in the sense that I have to generate a particular circuit node where, let us say I am doing a stuck at 0 fault, then the value that I should generate in the true condition should be 1, then the fault will be generated. It should be different if I am doing a stuck at 0. So, for generating a stuck at 0 fault at node C, choose a singular cover row which gives an output of 1 for the NOR gate and intersect with cross 0. So, what you get is PDCF is 1 1 D. What I am trying to do, if you consider this what I want is, this is a C node and I want to do a stuck at 0 at C. So when I have to do a stuck at 0 at C, I have to basically generate a 1 here, isn't it? If I generate a 1, then only a fault gets generated over here. Under fault and true condition and faulty condition, values are different. So to generate that fault, I have to go to the singular cover of the NOR gate, that is the truth table of the NOR gate, and choose a row in which the output is 1. After all, in a singular cover, the outputs are specified. Okay. So in this case, we know that for a NOR gate, output will be 1 when both the inputs are 0. So this I call it as 0, 0, 1. So typically when I am writing the D algorithm, I don't have to distinguish. So basically I have a node list and I write the values at the node list, and each of the values could be one of the 5 values that I have set. So 0, 0, 1. As far as stuck at 0 is concerned, here what I want is, I don't care what the inputs are, but I wanted a 0 at the output. That's what my fault requirement was. So I am going to cross this. When I cross this, I get 0, 0, D. When I do a D intersection of these, so this is node A, this is node B, this is node C. So this is a specification which is coming from the singular cover. I have chosen one row of the singular cover. This is my requirement. This is because I only wanted an output to be 0. I didn't care at this point in time when I wanted the output to be 0 what the inputs are. So I don't care what the inputs are, but I land up with 0, 0, D. I could write this as 0, 0, D complement, it doesn't really matter. Okay, both of them are at this stage it's equivalent. So I can just start from writing 0, 0, D. XX0 is coming from basically from my specification. What I require when I am doing a PDCA, what do I require? I require that this particular node should be stuck at 0. Okay, I don't care what the inputs are as far as my requirement is concerned. So that is don't care 0. Okay, but so I had to choose. So when I am doing a PDCF, I had to choose a row of the singular cover which has an output which is different from this. Basically, you can do this even directly. You don't have to do it as a D intersection. You can just choose a row of the singular cover and write it as all the inputs to be the same for that row, but output should be D. One value under true and another value under faulty condition. So I have this. So this is this shows me the, and this is called the PDCF.
If there are more than 2 lines, more than 1 line.
What is it?
So if there are 2 lines which give the same different output.
2 lines, yeah, you can choose any one of them, and there are options, and because we are choosing any one of them, there will be options, and we will talk about it. This is what generates the backtracking as far as the D algorithm is concerned. You can choose at this stage, you can choose any one of them. There could be multiple choices for PDCF.
So how do we do the D intersection in this case?
D intersection is just 0 cross 0 is 0, 0 cross 0 is again 0, and 1 cross 0 is D. Okay, so that is just, I am just here to D intersection when you are doing, you just have to read the elements of this table. Okay, of course this table you don't even have to remember, it's very obvious table. Okay, so when you are doing intersecting something, we don't care, the other value dominates. Otherwise you are only allowed to intersect only the same values. Because of the fault thing, you are allowed to do 0, 1 to D and 1, 0 to D complement. Okay, I think there is a mistake on this slide. So because I want output of 1, the NOR gate and intersect with, so this should have been 0, 0 D and not. NOR gate gets output of 1 only under the inputs are 0, 0. So I have this. So now let us look at another example of this. I could have been doing, for example, generating a stuck at 1 fault at node C. If I am generating a stuck at 1 fault for the same NOR gate, my PDCF will be different. So if it is A, B, C, and I am doing a stuck at 1, so what I want is cross 0, because I have a stuck at 1 fault. This is my specification, and to generate this 0, now you can see that there are, sorry, cross 1. Now I have to generate a 0 over here, so I can either do 1 cross 0. So this will give me a PDCF of 1 cross D. okay, because if I have this input 1, the output is going to be 0. Similarly, I could have chosen this one also, cross 1 0 also I could have chosen, and this would have given me cross 1 D. It does not really matter, you can write D or D prime. So, as I told you before, at this stage when you have only one D in your, let us say on the circuit node, it really does not matter whether you call it D or D prime. Later on you have to be consistent when they are relatively different, otherwise you can write it as D or D prime. Okay, so this is the PDCF. So now let us go to the last one, which is the propagation D cube. D signifies that that particular circuit node has a different value under fault condition and a different value under the true condition. The value of that node is different, and the whole algorithm is based on trying to push this node D to the output. Okay, so first of all you have to push this node D to the output, so that at the output I can see the output becomes sensitive to that fault. Basically the whole thing is based on, like even in Boolean difference we did the same. We want to make the output sensitive to a fault, and the output is sensitive to a fault if it behaves differently under the true and the faulty condition. So the propagation D cube PDC consists of a table for each circuit element, and which has entries for propagating faults on any one of its inputs to the output. See, now I have generated the fault. So I have to do the PDCF. When I do the PDCF, I generate the fault. The next step is to push this fault to the output, and to push a fault to the output I need to propagate this fault through the gates which come between this fault and the output, and to propagate this fault I have to use what are called the PDCs, propagation D cubes. See, the name cubes, please remember that the cubes are something like, when you call as cubes, they are essentially derived from the logic minimization. In logic minimization you have a set of nodes and you assign them values 0, 1, 2, 0, 0 or 1 or x. They all correspond to cubes if you consider them. You have minterms where all the values are assigned. Cubes are nothing but some of the values could be don't care. Okay. So here also they are called D cubes because of course the values could be 0, 1, D and D complement of course. So to generate PDC entry corresponding to any one column. So when I say column, what I mean is any of the inputs. So if in a TRIS table, what is the column? Of course there is also a column for the output, but we are only considering all the inputs. I should have a capability to transfer a D coming on any of the inputs to the output of the gate, and that is the PDC entry corresponding to any one column. D intersect any two rows of singular cover. Again please remember we are starting from singular cover which have opposite values 0 and 1 in that column. There can be multiple rows for one column. So let me illustrate what I am trying to say. Take a singular cover of the AND gate. So the singular cover of the AND gate is what I want is I want a capability. So this is my singular cover. Now I am doing PDC, propagation D cubes. What I want is if there is a fault appears with this input, I should be able to transmit the fault to the output. So I look at one row where this is 0, there is a row where this is 0 and another row where this is 1. Row 1 this is 0 and this is 1, and I cross these two, I take the D intersection of these two. If I take a D intersection of these two, what I will get is D 1. So what this allows me is of course you can argue it out even in a simple AND gate. You don't even have to do this. You know that if there is a fault appears here, this input has to be 1 for the fault to be transmitted to the output. But please remember this procedure is important because if your modules are complex, if you are only given a black box with truth table, you don't know what is inside. You should still be able to do exactly what we are doing. Okay, that's a procedure to generate these PDCs. So I have managed to get the fault here to this. Let me look at if the fault happens to be B. So I will look at a row in which this particular column is 0 and 1. So I have this row which this is 0 and in this one this is 1. I will take a cross intersection of these two. When I take an intersection of these two, I get 1 DD. So, to illustrate, so this is 1D and that's D1D. So, to illustrate what happens with D and D complement, let me take a NAND gate. If you look at a NAND gate, you have 0 cross 1, cross 0 1, 1 1 0. Again, if I want to generate, so this is my singular cover, if I want to generate my PDC, so I have to take this D1, now you have to write D complement, because it is 0 1 and this is 1 0. I have to write consistently. I can write this as D complement 1D, there is no problem. These two are equivalent for me. But I have to write here D complement and D. I have to write it reverse because it is 0 1 and it is 1 0. But it does not matter whether 0 1 I call D or 1 0 I call, that is no problem. Similarly, here it will be 1D D complement, and similarly I can write D complement 1D D complement. So, this is these are the what is called the propagation D cubes, and for each of the inputs I should have at least one row. I may have more than one row for propagating a fault on the input, but at least I should have one row, because if I have no row for propagating a fault from the input, if a fault is transmitted up to that point, I will no longer be able to get it to the output. Okay, so it is important that I should have at least one of the so this is called the propagation D cube. So, as of course this we have already considered, PDC of an AND gate with A and B as inputs and C as output is 1DD, D1D. We are already derived it. Similarly, for the propagation D cube for the NOR gate with A and B as inputs and C as output is 0D D complement D0 D complement. You can see that the other input should be non-dominating input. It should not be for a OR or a NOR gate, the non-dominating input is 0. For an AND or an AND gate, is the non-dominating input is 1. We are not limited by 2 input gates, we could do the same thing for 3 input gates. I will have, so I can do that for more than even 2 input gates, there is no problem. Now, let us go into the D algorithm and we will illustrate this with the same example that we were taking for the Boolean difference.
So when you PDC, so we have two expressions for those. Are those corresponding?
These two?
Yes, sir. So is one of them corresponding to an error at one node and the other at
No, PDCs, see right now we are not talking of error. PDCs are to be, see when you are talking of singular cover, when you are talking of PDCF or PDC. In all these cases, you are first generating these you can generate for all the elements, circuit elements by which your design is composed of. This is like more like a library. It is not something to be done online for each time, because you could have 1000 copies of the NAND gate and you do not have to generate each time. So, these are sort of something which is fixed, and it only depends upon the functionality of the library component. It does not depend upon the actual. So, when I am going to write my D algorithm, I will choose one of these rows as it is convenient what I require. For example, a fault has been propagated to this input and I want to get it to the output, then I will use this row. But if the fault has come to this input, I have to use this row. I will select one row of PDC, any one row of this. In case of PDCF, of course, there are two types of entries here, one for stuck at 0 at the output, one for stuck at 1 at the output. And in each case, I could have again multiple rows which are first stuck at 0 or stuck at 1. And I have to choose one of these as it is required. And sometimes we will see that when the multiple options are possible, then the backtracking may be required if consistency fails. We will consider that in an example later. So, now let me go through the steps. So, we will of course illustrate these steps. So, let me just choose a stuck at fault at any of the nodes, whichever node that I want to generate my test input pattern for Basically what is the problem I am solving? Given a fault, I am trying to identify one or more test inputs which will be able to detect this fault. So I choose some stuck at fault at any of the nodes. Choose a PDCF for generating the fault. PDCF is to be used only once for generating the fault. So this particular fault, there is some element and I have chosen a stuck at 0 fault here. It may have 2, 3, any number of inputs. So I will choose a PDCF of this particular gate so that I get a fault over here. What this will do is this will specify something at the input. Some of them maybe don't care also, but some specifications will be there at the input and there will be a D at the output. So when I choose a PDCF, and for PDCF for this gate, whichever gate or whichever element, circuit element that is there. If I am doing for a primary input, you may say that if I want to do a stuck at fault at a primary input, what do I do? You can just assume that there is a buffer which is nothing but it just follows the input and use the PDCF for this. Basically a PDCF for this will be nothing but the opposite of whatever is the value. If I want a stuck at 0 here, primary input should be 1. If I want a stuck at 1 here, the primary input should be 0. So if it is a primary input, you have to do this. If it is a, just assume a 1-to-1 buffer which just takes the input and but if it is an intermediate node, then I choose the PDCF. So choose a PDCF for generating the fault. That's the first step. So now second step is choose an output or choose the output and a path to the output and propagate the fault to the output by choosing PDC for all circuit elements on the path, one by one. So I choose one output where I want to see the fault. Typically the way it is done is, if there are multiple outputs in a circuit and these outputs have different path lengths. What we talk of path lengths is in terms of the number of gates that appear between this node and the output. The number of gates which appear is larger, we choose a path which the number of outputs is smaller. Gates on the path is smaller from this particular node to the output. If some output has 5 gates between this node and the output and another output has only 2 gates, I choose the one with the 2 gates first attempt, because it is more likely that I will be able to propagate it without problem of consistency. See, this is a consistency thing is important and we will come back to this, because you can always propagate but you will not be able to get a set of primary inputs which are consistent. So I choose an output, again I will show this as an illustration, and a path to the output and propagate the fault to the output by choosing PDC for all circuit elements in the path. You may have options in terms of outputs, you may also have options in terms of paths. So here at both these places you are making a choice, and if this choice is not successful, you may have to do backtracking. You may have to make another choice and perform this. So once I had done this, and this is called the D drive, I got the D driven to the output, use the singular cover of all unassigned circuit elements to arrive at a consistent set of inputs, and this is called back propagate or consistency check, and we will follow that example and illustrate this, and then these points that I tried to make here would become clearer. So the same example, I have A, B, C, D, E, these are 5 inputs, primary inputs, F, G, H and I are 4 gates, outputs of the 4 gates, 1, 2, 3, 4 that I have. So at any point in time, I will have a 9 tuple where, because there are 9 nodes here, which will define the state of this, or which will define the values at each of the nodes, where each of these can take a value 0, 1, x, d, d complement. So if I write a string of these 9 values, then I have a particular value assigned to each of the nodes, and I will just follow that in A, B, C, D, E, F, G, H. I will not write each time, but I will just follow that in that order. So choose a fault, say G stuck at 0. So because I have chosen a fault here, G stuck at 0, I have to choose a PDCF for gate 2 for generating this fault, and the PDCF for gate 2 will be, because it stuck at 0, I have to generate a 1 over here. Okay, to generate a 1 it is 0, 0. So I have So this is A, B, C, D, E, F, G, H, I. So initially I start with all x's, nothing is specified, I am starting with all x's, and once I have chosen a PDCF and crossed it with this, I get 0, 0, D, where D, E is 0, 0 and this one is D, and so I have got the PDCF of this. So that is the first stage. Now I have to do the D drive. So to do the D drive, what I have to do is how I am going to take this D to the output. I have to choose an output. In this case I have no choice, I is the only output, and I have to choose a path. In this case it happens to be there is no choice in the path. So I will drive this like this. So if I am going to drive this D to the output, I have to propagate this fault through gate 3 as well as gate 4, and for this propagating the fault I have to choose the PDC propagation D cube for each one of them. So I have this 0, 0, D and I have to choose the propagation D cube of 3. So now when I choose the propagation D cube of 3, so what is the propagation D cube that is relevant here? Basically I have 3 nodes here. If I look at the PDC of this NAND gate, please remember this NAND gate actually the inputs are F, G and H. So the PDC is D1 D complement, 1D D complement. As far as F, G and H are concerned, and as far as this PDC is concerned, all the other values are don't care. Okay, as far as this particular propagation D cube is concerned, only these 3 values are specified, D1 and D complement, 1D and D complement. So one of them I have to choose. So I have to choose the one in which G is D, because this D is, I cannot cross this with 1. Please remember the D intersection, I can only cross it with D. So I have to choose something which is, so I have to choose 1D D complement, which will give me this, and when I cross it with this, so F becomes 1. So this is A, B, C, D, E, F, G, H. F becomes 1, this becomes D complement. And when I cross it, I get cross 0, 0, 1 D, D complement X. So now I have got this D up to this, D or D complement does not matter, here I got the fault transferred here. Now I have to transfer the fault to this, to the output, because this is the path, please remember I chose. So I have to get this one here, so I have to choose the PDC propagation D cube for gate 4, so that I can transmit the path fault here. So here if you look at the PDC for OR gate, 0 D D, D 0 D, where this inputs are A, H, I. But I already have H to be specified to be D complement. But here what I can do is, because H is D complement and I cannot cross this with D, I can actually convert this into, this is what I said, I can call this 0 D complement D complement. When I take this row, I have no problem in just calling all the D's to be D complement and D complement. I should do that consistently. So I take this row to be, this is my, this please remember this is all PDCs, propagation D cubes for the OR gate. So I take this 0D and cross it with this. When I cross it with this, I get 0 D complement and I get 0 cross cross. B and C as that are not specified. So I got a 0 here, I got a D complement here. 0 cross cross 0 0 1 D complement, and my D drive is over because my fault has traveled to the output. Looking at this, if I put a probe over here, or if I can see that, looking at this output I will know whether the fault is present or not. But the whole problem is not over. The problem is not over because I still don't have the primary inputs. Of course, more than primary inputs, of course, inputs can be don't care, but I don't still have consistently assigned all the inputs to the gates. This particular gate is still left. I don't know how do I generate this 1 for this. I have to generate a 1 for this, and this is the problem of consistency. Look at all the unassigned gates, and you have to go now from, like here you are going from this node, from the faulty node to the output, but now you have to go back. That is what is called back propagation. Look at the output. So, in this case this was 1, this is D complement 0 D complement. So, I have this 1. So, now I will not look at the PDC, I will now look at the singular cover. I only have to look at the truth table, I do not want to now bother about the faults. I want to assign the inputs in such a manner that I am able to generate an output of 1 itself. And if I look at my singular cover for the AND gate, the only entry which generates the output of 1 is 1 1. So, here SC is nothing but 1, sorry, don't care, 1 1 0 0, sorry, don't care, A B C D E F, F is 1, and then don't care. When I cross this, I will get this 1 1 0 0 1, 1 to 1 has to be crossed, D complement, and I have assigned, there is only one gate which was unassigned. So, after doing this, I get my primary inputs 0 1 1 0 0, and that happens to be the test vector for my fault to be tested. This is only one of the test vectors. So, whatever I have done over here, I am representing that, and this is how you can do that. This is what actually happens even within a machine when you do this DQ. So, it is all done in one single table over here. So, you start from an initial where nothing is specified, all of them are don't care, whichever the fault. So, there is only one entry over here which is PDCF2. This need not even be written, this is assumed that. So, I just started with this, but you do not have to really write this. So, PDCF you choose. So, PDCF when you choose, it is cross cross 0 0 cross D cross cross. So, that is the PDCF2, and once the PDCF is done, then you do the D drive. The number of rows for the D drive will correspond to the number of gates that are present between the faulty node to the output, and in each row you take some gates. So, in this case you have taken the propagation DQ for 3, which is consistent with whatever you have done till now, and cross intersect with it, and then you get this. So, in this case the two additional nodes that I got specified are F and H. Now, you take the next gate in the path. So, PDC of 4, and then you cross it with this. In this case what has got specified is this and this as additional. My fault has reached the output. So, my D drive is over. Then I do the consistency check, and I, of course, all the gates that are remaining whose outputs have been assigned, but inputs have not been assigned, they have to be followed with the consistency check. Yeah. So, in this case what has happened is, after performing this D drive, I have an output 1 assigned to this particular AND gate, but I have not assigned any inputs in the D drive, because it did not, because this was the path. So, I am just looking at the paths and assigning the other inputs which are there in the gate in the paths to some value. Sometimes I may be assigning don't care value. If I am assigning a don't care value, the inputs are also don't care. But in this case I assigned a specific value of 1. So, I had to assign my inputs in such a manner so that I can generate the value of 1 over here. And this is the way it will back propagate. Wherever I assigned, it will back propagate. And so, in this case I have assigned 1 1 to generate. So, this I do using the singular cover, and that is what is the consistency check. See the way this particular procedure. So, in this case in one shot I have been able to find. Please remember, I am not interested here in finding all the test vectors for this fault. And the other thing is, at each stage when I have multiple options, either in PDCF or in propagation DQs or in consistency check, and even before that choosing an output and a path, at each of these 5 stages I may be making choosing one of the options available. It may happen that when I choose such an option, finally consistency may fail. Consistency can typically fail. I will take up an example like this. If you have multiple paths, this is called a reconvergent circuit, where you are taking an output and it is following a path and going over here, and to satisfy one path you have to make some assignment, but to satisfy another path you have to make a different assignment to the same input, then your consistency may fail. And then you may have to backtrack and choose an option which you have not chosen, and that may actually result in a, if this particular point is testable, the algorithm will of course finally find a test input. But if the node is not testable, if there is no way I can transfer the fault to the output, the algorithm will fail. But you may have to do backtracking, you may have to choose the other option that you have not chosen or the other path that you have not chosen and perform this. We will see an example of this later. Okay, that is well.